Welcome back. So, in previous lecture we discussed about different type of seismic waves, body wave and surface waves, and we also discussed briefly about their about their motion mainly. And coming to the last point which we left out was the earthquake prediction and forecasting. And as I was mentioning that the forecasting mainly identifies both earthquake prone areas and man-made structure, because mostly we are concerned about that what will be the damage which will take place because of the ground shaking. Now earthquake prediction basically is that if we can precisely estimate the event, but in the complex nature of the earth crust and the heterogeneity which exists within the rocks and all that, it is sometimes difficult that whether the earthquake will occur at the same interval or not. So, that is one of the limitation. Another limitation is of the dating the earthquakes or the events, that we will talk when we are discussing the paleoseismology part. Now, the idea is that if we do the prediction, then on which particular fault the earthquake will occur, that is the important part. So, in previous lecture we saw some figures where I was trying to show you that there are different fault lines within the fault zone, and those fault lines slip at different rate. Now, coming to the other part of the earthquake prediction and forecast. So, earthquake forecasting is based largely on elastic rebound theory and plate tectonics. So, the elastic rebound theory suggests that if fault surfaces does not slip easily past one another, energy will be stored in elastically deformed rocks, just as a steel spring that is compressed. Okay. So, what basically this means is that if the fault plane is locked, or the two blocks which are adjacent to one another along the particular fault plane, then they are not slipping, but at the same time, because of the continuous ongoing deformation, it will keep storing the energy, and that energy has been stored in elastically deformed rocks. So, after the threshold limit, they will slip and result into the earthquake. So, if you use this deformation, that is elastically deformed rocks, and the energy which is getting stored, which can be measured with the help of the GPS stations. So, continuous GPS stations if you are having, so that can help you in understanding that which portion of along the fault line is getting compressed or is storing the energy. And so, along with the paleoseismic studies, GPS measurements is extremely important, because they will help us in monitoring the accumulation of strain in rocks near the active faults. So, in most of the countries, even like now we have started in India also since last couple of decades, I would say that almost like past 10-15 years, the GPS installation has been intensified, and that has been done under the flagship project of Ministry of Earth Science, and many stations have been installed which are doing 24/7 recording of the coordinates in Andaman, and that was done after 2004, and even after 2001 Bhuj earthquake, lot many stations were been put in Kutch region by Institute of Seismological Research, and mostly in Andaman, Survey of India and other agencies like NGRI, National Geophysical Research Institute, have installed their stations, GPS stations in Andaman also. And in coming to the Himalayan part, many stations have been installed in the central Himalayan zone, and we at IIT Kanpur we have installed almost like 15 stations, and we are going to install more, and these are all permanent GPS stations. So it will keep on recording the coordinates 24/7, and the any movement or any deformation which is taking up in the crust will be recorded, because the coordinates keep changing, and based on that one can easily make out that which area is deforming with a higher rate and which area is deforming with the lesser rate, and that will help us in understanding the pattern of strain accumulation in different blocks in the tectonically active regions. So what we did was that we have taken into consideration the active faults, because these are the areas where you will expect the next earthquake. So the aim was to tap such features on the surface, and the GPS stations were been installed accordingly. So based on this recording also one can understand that for which area is going to trigger the future earthquake, in particularly in seismically active zone regions. Okay. So how it works? So if you look at the sketches which are been, or the diagrams, schematic diagrams which are given here, it shows that there is a fault line here. So this is a plan view, and any man-made structure, and as I was showing you in the previous lecture, that even the landforms, the naturally formed features on the earth's surface like drainage or the surfaces, they will get deformed because of the ongoing deformation. So this is an original position of the fence and the fault line, and since the deformation is ongoing, before it finally slip, it will get deformed depending on the what is the moment along the fault. Okay. So this, it shows the right lateral where this block is moving towards right, towards us, and this is away from us. So this is a right lateral one. So fence will be deformed like this. Okay. But this process is very slow, so you cannot make out easily by a naked eye. So GPS, if they are, for example, if they are installed, for example, one GPS has been installed here and another one has been installed here as well as here, then this GPS stations will be able to will help you in understanding, because the position of the GPS will keep changing. So if you are having one is here, another one was here, and third one is, for example, here, and you can have one more here also. So basically what we have done in Himalayas, that we have taken into consideration the fault lines, and across the fault lines we have tried to install the GPS station. So this coordinates will tell you, change in the coordinates will tell you that how much amount of slip has been accumulated, or what is the pattern of deformation and how much strain is getting accumulated along this fault line. And finally what we see is the rupture. So this is the process of deformation, which may take 100 years or more than that, because in Himalaya what we have seen as that the recurrence of the earthquake is almost like 500 to 600 years. So the ongoing deformation can be easily picked up based on this, and whatever the deformation will occur, like the slip, final slip or rupture in the release of the energy, this is release of the energy is your earthquake. At that time you will also get things recorded in the GPS, as well as they will be also the manifestation on the surface will be seen in terms of the displacement of the landforms and any man-made structure. So it shows that there is a deformation which is elastically deformed, then there is a rupture, and then it rebounds, because the material are having some elasticity, so they will try to rebound to original undeformed shape, but then the slip which has occurred, So we will see the residual slip has been left out, and this deformation will get preserved on the surface. So rocks near a fault are slowly bent elastically, that has been shown here, until the fault breaks during an earthquake. Okay. And when the rock on each side slip past each other, revealing the stresses. Okay. So this is what has happened here in the D. So this process remains very much similar in any type of deformation regime, either it is compressional or it is normal or extensional or strike slip regime. There is another example of San Andreas fault system which has been shown here. Okay. So you have some man-made structure which will get elastically deformed and finally it will break along the fault. Now this was observed in 1906 San Francisco earthquake along San Andreas fault system, where the fence got offsetted along the fault during 1906 San Francisco earthquake. So how GPS can help, and this has been shown here again along the or across, we can say, across the San Andreas fault system. So what they have done is they have put number of GPS stations along the across the fault line along the same transect here, and you can see that this is the fault line which was been marked. Okay. And the same pattern or the methodology we are also following in Himalayas, that we have the fault trace and we want to monitor that what is the amount of strain which has been getting accumulated along the particular fault region. So now if you see, there are from 1 to 15 GPS stations which have been installed here and which shows different movement. So this is what you are having, the maximum offset has been seen along between this one, okay, and this is your fault line here. So the photograph which shows the aligned deployment of the GPS station, a number of numbers are located on the right. So these are the numbers which have been given here, 1, 2, 3, 4, and you can see the car as in scale here. Okay. So the B example, this is after the measurements. What they have observed is the alignment array offset analysis along the Mee Ranch area. So the upper panel, which has been shown here, okay, shows the monument located in the in fault centered reference frame. Okay. So these are this is the fault here, and these are the stations which you can see here. Okay. So these are all which shows the offset. So initially there's all stations were in the same line. Okay. So this was the transect, but now after the deformation, what they are able to see is the displacement. So the maximum offset they were able to pick up was almost like 905 millimeter between this one. So this is an offset along this line. Okay, so this shows the fault plane fault parallel displacement or the distance. So along which this two array of GPS are been shown here. Okay. So maximum displacement was the almost like 905 millimeter, whereas the end points or the end offsets. So what it suggests is that the displacement or the deformation is slightly variable, but of course with the help of this one can make out that what is the amount of strain which is getting accumulated along the active fault lines. So in one of the slide we also discussed that if this and the rock strength remains the same, the material which is under deformation remains the same, then we will have a very typical like time lag between the two events. So, this will be the time of the strain accumulation, and this is the event. This is the time of accumulation, this is the event. So, this will be very systematic, but this never remains the same because of the heterogeneity of the material, as well as the rock strength will change over the time because of the fracturing or the displacement which has been taken up by those rock blocks along the fault zone. So, this we already discussed. Now, I will show a couple of pictures if possible in the next slide, that how this different faults are behaving, and particularly we will talk about some signatures of this fault, Hayward fault, which is creeping basically. So, creep along the San Andreas fault system, that is along the Hayward fault, which is a part of the larger fault system, that is San Andreas. Okay. So, people stay here in this region, and the fault goes along this line, and but now since they have confirmed that this is an active fault, no construction has been allowed here, but those who are staying here, they understand the hazard along this fault, that is Hayward fault, and since it is creeping, one can easily pick up the deformation which is either seen in the displaced walls or either seen on the pavements, as well as the pedestrian pathways which are getting deformed over time. Okay. So, the pedestrian path, if you can see, this is completely getting folded here or offsetted here along this one's fault lies somewhere along this line here. So, if we put the fault here along this one, this is what the boundary it comes to. Okay. This is an offset. Okay. So, this block has moved in this direction, and this fault is creeping, Hayward fault is creeping. So, one can make out that how much the deformation has been consumed by this. Okay. So, local people who are staying here are facing problems, but this, with the understanding, they are trying to cope up, that how they can fulfill and make their structures more stable or safe because of this ongoing creeping. So, the utilities like pipelines or the gas pipelines or the sewer lines, or maybe you can say the water pipelines, they have kept it something in a very elastic nature of the pipes are been installed, so that this can be, this creep is been consumed because of the displacement along the Hayward fault system. So, this is another example of the same region which shows the displacement, and the fault runs somewhere over here. This is one portion, another one is coming over here. So, they keep on repairing this. So, I will show the close up of this one, and you can see the shear fractures which have been formed because of the displacement which is occurring along the Hayward fault. Okay. So, this is the close up of that pavement over here. This is the this portion in the next slide. Okay. So, this of course is was on horizontal or straight feature, we can say, which was going like this. Okay, but now it has got displaced this much. So, this is the displacement, amount of displacement which has occurred over the time. Okay. Similarly, because they are having the understanding of the ongoing deformation along this fault, what they keep doing is, because you cannot like fly over the fault, but you will have to survive along with the fault only. So, if you see the offset here of this rail track, these are the older rail tracks and they have been replaced by the newer one. Okay. So, by the time this will get deformed, they will replace another new one along this one, so that the transportation is on every time. Okay. There is a close up of that. So, the offset, you can see the fault runs somewhere over here like this. Okay. So, you have an offset of the So, this is because of the creeping. Now, since this creeping is comparatively faster, so energy is not getting stored along this fault, but it is been slipping. So, this is very fast in terms of the overall deformation. So, of course, the overall slip, if we take, is around 9 millimeter only. So, the overall fault is not slipping so fast, but the creep what we see is been manifested on the surface, and that has helped in understanding the ongoing deformation pattern in this region. So, this is another example of the displacement offset in 2004 and then offset in 2006. Okay. This one is another example where the water pathway or the drain way has been offsetted along the San Andreas Fault systems, the Hayward Fault. Okay. So, in many regions like San Francisco as well as the Hayward Fault here, they know that where exactly the fault lines are passing through, and they also know that what is the amount of slip that has been taken up along the respective faults. So, this is what they say, a giant crack in the earth, that is your San Andreas Fault system is crossing beneath many of the cities. Okay. So, this is an example from the Seattle, where the major fault or Seattle Fault which passes through. So, they also know, and then the construction or is been done accordingly, keeping in mind that what will be the magnitude when the next earthquake will be triggered along that particular fault. Now, looking to the GPS part, this is what it can help. It can also make us understand that what is the velocity of at different points, and if you are having a close array of the GPS networks, and then you can also make out that how individual faults are behaving. Now, if you carefully look at, then most of the part which is sitting in India is not having many GPS stations. So, this figure is of course a bit old, which does not show the location of the GPS in this region which are already been installed. This is Nepal part. So, in Nepal we have many GPS stations which are recording the ongoing deformation in Himalayas, but now we are covering this part, and then some agencies, the institutions have taken up putting the GPS stations in Kashmir region also. So, the strain accumulation can help in predicting and forecasting the earthquake if we take the GPS measurements. So, we have like two type of information with us. So, one is we are doing the paleoseismology. Now, this will give us a long term deformation, and then second one is your GPS. So, GPS will give you short term because in paleoseismology basically we are going to look at the deformed landforms. So, this deformed landforms are definitely during the previous earthquake. So, more than 500-600 years old, or at least what we have been talking about since beginning, that at least the deformation goes back up to, if it goes back to 10,000 years. So, in that sense we are talking about the long term deformation, whereas this we are saying we have started recording since last 50 to 60 years. Okay. So, this two type of the information we can gather, and when this and both of them complement each other actually. So, we understand with the based on from the paleoseismology we understand the long term deformation, and with the GPS the present deformation, ongoing deformation, which can be picked up as what we call the short term deformation. So, these two part goes side by side. Along with this, we also will get and like we can use the seismic networks also to understand the distribution of earthquakes and all that, and that can also be taken into consideration when we are talking about the overall hazard assessment. So, long term we are having from the paleoseismic studies, because we are going to study the landforms, and short term is the GPS measurements we do. Okay. So, these are the two important pillars which can help us in identifying the pattern of deformation. So, earthquake prediction has had few successes, okay, and one of the best was from China, which I'll just immediately talk about. But mainly what the successes is been achieved until now is based on the precursory events. Okay. So, and then one can also look at the suspicious animal behavior, then unusual electric signals. Many large earthquakes are preceded by small earthquakes called foreshocks. So, if you do continuous monitoring of the foreshocks, or because you doesn't know that whether this these are the foreshocks or now the main shock will come. Okay. So, there is no like you cannot conclude it, but at least you keep on monitoring the micro seismicity, and if there is some unusual pattern which has been observed during the recording, then you can try to predict the future or forecast the earthquake actually, and these are all short term predictions. So, many large earthquakes are preceded by small earthquakes called foreshocks. Chinese authorities used series of foreshocks as a warning to anticipate the Haichen earthquake in 1975, and they were extremely successful in this. They were been able to predict this and they forecasted this, and that was been done based on the analysis of the small magnitude earthquakes, which because there was a main earthquake which was triggered, and they categorized those small earthquakes as in foreshocks. Okay. Major and great earthquakes in Himalaya. So, another study which also highlight that there was successfully they were been able to identify and predict the earthquake, major earthquake in Himalayas. So, if we look at the information which is available other than what we have been talking about, and few of them are listed here, but we discussed about some historical data also. But if we take the good record, in the sense we are having the at least latitude longitude of those earthquakes and the magnitude also, then we have like from 1897 it goes back into the 1952. So, these are the locations of those earthquakes. Large earthquakes, as I was talking about, that we had like in 20th century. If you list down this one from here, from since 1905 we are having many earthquakes which have occurred with a magnitude greater than 7, and some of the earthquakes have been assigned like magnitude above 8.5. This was been resized, that is Kangra Valley Fault earthquake, which was been resized to 7.8. But anyway, if you see those this listed earthquakes, then they are above 7.5, all are above 7.5, and most of the earthquakes which are recorded are from the 20th century. And so, we if we have more data from the paleoseismic investigation, we can easily have the somewhat complete data set of the seismic events, can help in better prediction. So, these are the three major one which have been shown by black dots here, along the Himalayan arc, and this is slightly away from the Himalaya, that is 1897 Shillong earthquake. So, what it was been observed, considering this available data, that there was a period of quiescence where the 7.5 magnitude above or equal to 7.5, almost 14 events have occurred between 1897 and 1952. Okay. So, almost 14 events, but from 1953 onwards until 2001, no earthquake has occurred. Okay. And of course, if you try to incorporate more data, then we have after 2001 the magnitude above 7.5, we have 2005 Kashmir earthquake or Muzaffarabad earthquake, and then another one is 2015 Kodari earthquake or Gorkha earthquake we are having. So, those two will be added here, and then with the magnitude ranging from 7.5, that is greater than and less than equal to 7, 11 events have occurred during this period, and 7 events have occurred during this period. But and similarly goes for the less greater than equal to 6.5, we have 19 events, and then we have 21 events. Okay. Now, the number of occurrence of this earthquakes with magnitude around 6.5 is not going to suffice the amount of energy which is going to be released during this magnitude earthquake. So, many earthquakes will be required in terms of number to suffice this one. So, this still remains the gap here. So, this is what has been told, that the quiescence of major earthquakes since 1953 and 2001. So, I will stop here and we will continue in the next lecture. Thank you so much.